Okay, so this is the tangency and intersection file. I'm going to record a few of the aspects of this file that we went over in class. So here are different types of cones. So there's this is a right cone with a 90-degree angle, and this type of cone is useful because it can make, if I extrude surfaces that are tangent from it. You could imagine this type of cone. Fits nicely with an orthogonal architectural system. Okay. Then this is what's called a right cone. This is where the apex is over the middle. This is an oblique cone where the apex is off to the side. And this is a general convex surface, which is just any curve extruded to a point. And this right here is a sort of a special cone that has one vertical axis. So if you do line vertical from somewhere on the cone and you extrude that to a point, this cone is tangent to a vertical wall. And oftentimes these are very useful in people's studio projects because you often want to transition between something that's tilted to something that's vertical smoothly. Okay, so the easy way to make connections between two surfaces with cylinders and cones is to use this fillet edge command. So you can just take two surfaces, join them, fillet edge, click on the edge, and then you can enter a radius. And you might have to enter the radius first rather than clicking. Yeah, I think you have to go enter the radius now and then click on the edge. And then if you click on one of the handles here, you can change the radius. So I could make this 25, 25. That's a cylinder. Or I could do, let's try 30 and 0. That's a cone. Okay. So that's the simple, silly way to make it. Here is the general principle, which is that if you have a cone, it is it's tangent to another cone or another surface that is developable. If it is developable surfaces, if you recall, are surfaces that can be unrolled planes. So they have an intrinsic flatness. They're not like spheres. They're not puffy. So this surface is tangent to other surfaces like that, planes, cylinders, cones, other surfaces that have an intrinsic flatness. If its apex is along one of the edges of the other surface. So let's do a circle tangent here, like this from first point, make a circle, and split this. I can extrude it up like that, and this cone is tangent to this cylinder. It's also still tangent if I move the apex. It's also still tangent if I move the apex down here. It's also still tangent if I flip it upside down. And the same would be true for cones. This cone was extruded there, and extruded there, and extruded there. All of those are tangent. So is the opposite one. If I were to extend this line down and extrude it to a point, these are also tangent. So that is the gesture that you use to flip from tilting this way to tilting that way. You have these opposite cones like that. Okay, so that's the general principle. Then in terms of this category is about transitioning between one shape and another. So if I have two shapes, I'm gonna do a different one. Let's say I have a triangle. Let's say I have this weird, let's say I have a triangle like this. If I make a tangent tangent, 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 like that. And I split this triangle at the moment of this circle at the moments of tangency, and this triangle at the moments of tangency. And I move this triangle up in space and extrude these curves to those points. And then I can fill in, I didn't actually need to split the triangle. I can fill in that way with planes. So by splitting at the moment of tangency, I can fill in with planes, and that's sort of a developable version of something that would be a loft between two surfaces like that. This wouldn't unroll flat. The other version, if I were to join all these surfaces to each other and go unroll surface, uncheck this explode, I could go find that, and you can see that that unrolls flatly. So that is about transitioning between shapes. Here are some other ones. This is going to a square. I'm going to see about going to a random polygon, show you a difficulty that arises there. I have a random polygon like this. I'm not going to be able to be tangent to the third side. So in order to fix that, I have to do something like this, make a tangent line like that, extend this, split that like that, rejoin it. Then I could split this sphere, this circle at all the tangent moments. Then I could move this up in the air. And then I could extrude these again to the points. And I could cut this, lower down. And it would be a smooth loft. Okay. So that's that. That's this category. The only other thing that's here are the sphere cone and tri-cylinder. So the sphere cone is a 90-degree cone based on that. I have this 90-degree cone and I mirror it. I'm using this mirror 3-point, so I can mirror it about a plane. And then I split it in half. And then I rotate it 90 degrees. You can get that thing like that. That's what's called a sphere cone. This is sort of interesting, I think, only for you guys, unless you happen to like it a lot, because you can see some sort of interesting properties of cones. Here you can see that these two 90-degree cones have sort of enabled me to go from back to very architectural things very quickly. And so also, if I mirror this, you can see I can get these sort of cusp type intersections with cones, where two cones sort of diminish smoothly to a surface like that. So these are sort of interesting properties of cones. If I had something like this, this type of right cone connection, I could scale that. I could remove the apex. Becomes a very sort of interesting architectural condition quite quickly. Also, I can put other types of surfaces in here. I could, if I extrude this, this way. That's a piece of a cylinder that also fits in there. So these surfaces can sort of be put together in many interesting ways. And if they intersect, you can sometimes get and share. If they intersect and completely share an edge, you can sometimes get these diminishing lines. So another way to get that would be if you had a cone that went I wanted to make a vertical cone. If you had a cone that went to a point vertically, like so, and then you had a different cone that also went to a point along that edge. You will see they have, again, this diminishing intersection. And that is difficult to resolve in practice. What you need to do in order to get it to happen is if I intersect these cones, Rhino won't find the complete intersection. So often you'll have to do a plane 3-point. If it's a planar intersection, to sort of complete the missing part, and then actually split the surfaces, not with the surfaces, but with the curves, in order to get them to join like that when they have this diminishing edge. But that can be quite beautiful in various conditions, because you could pull a vertical wall off of that moment. Okay, so that's that. All right, let's look at making tangencies now. So how do you do that? There are a couple of different ways. This category I've called tangency in a plane. So I want to look at a few of these examples. So if I have a cone here, I can extract an isocurve or split it. I'm going to split it like so. And then what I can do is I can use line tangent. So what I often do is I often type line to make guides, and then I use one of these particular constraints. So here I can make tangent, and I can do from first point. I can do another one, tangent from first point. Excuse me, that's an error. So in order to make a surface that's tangent here, I have to first extract an isocurve. Extract isocurve, and the other tangent would have to come from, it's hard to get this to work, would have to come there from first point, from the same isocurve on the surface. Otherwise, it would not be smoothly connected to the surface. So if I make a surface along here, there are many ways to do it. I can go extrude curve along curve and extrude the isocurve along that surface. Or I can put a plane here, surface plane 3-point, 3 points like that. All of that works. So another way to do this would be to actually extract isocurves and split the surface beforehand. And then I can simply go curve, extend curve by line, and I can extend a tangent that way, extend a tangent that way. And then I can explode these. I can loft that, I can loft that. Lofting doesn't guarantee you to make a plane. However, in this case, because these lines are parallel, it would. A safer way to do it is usually surface extrude curve along curve in case you made a mistake. So that is the simplest way to make tangents. That is, if you have a planar cut of a cone or a cylinder, You can do the same thing with a cylinder. You can just extend tangents from the profile, from the planar profile, and make a surface that's tangent that way. Okay. Then in order to go tangent to some of the other types of extrusions or conics that we were talking about, basically I can go to this condition, and then if I were to draw a random curve here instead, I could use this curve tool or type curve. And that is, we'll go over this next class. It's a spline curve, has a degree 3. And so these are tangent to a line if the first 2 points that you click are along that line. So basically, if I click on this curve, you can see you can turn the points on and move them around. And after the first 2, anything can really be done with the curve, and it won't affect its initial tangency. But it's these first 2 points have to be somewhere along this tangent line. And then if I have that, I can extrude that curve along the edge of this surface. And that will be tangent to the original surface, like that. Or if I want it to be a conic surface, I can also do the same principle and extrude that curve to a point. That point would be along the edge of the surface that you're attaching it to. So that would be the same principle that we talked about here before about sharing an edge. You would, if you're doing a cylindrical surface where all of the lines are parallel, you extrude curve straightly or a long curve along an edge. If you're doing a conic surface, I'll do one over here. You can extend the edge and you extrude to a point along that edge, like that. Okay. So that's what's going on here. And then the next thing is those are all, planes, tangency in a plane where you're drawing a curve that's tangent in a plane that is shared by a cut of the profile. A more flexible way to do it is to use some of the intrinsic properties of the surface. So that would be the normals or the isocurves or of the surface itself. So if I have a cone like this, I can extract an isocurve. In this case, it's already been extracted. It's this edge. And I can just rotate the cone 180 degrees about the isocurve. I'm going to cut it, undo, and paste. There you can see rotating 180 degrees about the edge of about an isocurve makes the surface tangent to the surface that it came from. And I will do this a lot, and then I will modify that surface by scaling it or moving the apex. The same thing would work, by the way, with a cylinder. If I had a cylinder here, I could rotate 180 degrees about one of its isocurves to get a tangent cylinder. Like that. So why does that work? It's because these are surfaces of revolution, and if they are tangent, there's a connection between the center of one and the center of the other that is created by rotating around 180 degrees. The other way you can do it is you can draw the normal like that, and you can rotate this 180 degrees about the normal, and that surface is also tangent, all like that. Okay, so that is using rotation, which is sort of like a quick version of the next category, which just uses the normal itself as a way to construct the tangency. And in order to do that, essentially, if I have, I'll do this one, I'll do this one, and I'll do this one. Okay. If I have two surfaces and I want to make them tangent, I need to sort of get a local coordinate system on the surface and align it with the local coordinate system of the other surface. So I need the information of the surface at a point. And that is the isocurve at that moment. And it's the normal at the moment that I want to make tangent. And then sometimes it's also the tangent at that moment. So in order to find that, there I would, extract an isocurve here and do line tangent. From first point. Like that. So that is sort of, look at it, sort of a local coordinate system right there. You could also get one of the one, if you only had two, you can get the other one by rotating it 90 degrees about the other one. So there's a little local coordinate system here. And in a twisty surface, that coordinate system changes very quickly as you move around the surface. But in a developable surface that you can unroll flatly, it is the same along any isocurve. So like if I move this up here, and I move this here, and I move this here, and I move it here, it's still basically the same. So I can do the same thing with this surface. I can extract an isocurve, and I can get a normal there, like that. And then all I need to do to make these things tangent with each other is align one normal with the other. So I can go transform, orient, 3-point. And well, actually, I want this point to be here and this surface to be this way. So if you'll see, if I do this, I go transform, orient, 3-point, pick this point, pick a point along the normal, pick a point along the isocurve, pick this point, pick a point along the normal, pick a point along the isocurve. There, it's aligned perfectly like that. If I wanted it to be aligned, though, in the other direction, I could do it with the normal, the other direction of the normal. So I could go transform, orient, 3-point, pick a point there, pick a point in the normal, pick a point along the isocurve, pick a point there, pick a point on the normal, pick a point on the isocurve. And just like I could slide that coordinate system up and down, I can slide this up and down. And that goes back to the same principle that we talked about here of as long as the apex is on an edge or they share an edge and extrude in the same direction. So that's that. I can do that with a plane and a cone. I can get the normal. I can get an isocurve. You can get the normal. And then I can transform, orient, 3-point. Pick a point here, put these on the layers. Transform, orient, 3-point. 1, 2, 3, 1, 2, 3. Because this is a plane, I could have also used a different line that is also in the plane. There we go. And then once I have this aligned, I can do what I've been doing before, to keep going. Like that. Okay, and now let's do it again. Line, normal, curve from object, extract isocurve, line, normal. I can align that, orient 3 point. And they're in the same spot, so if I wanted them to be the other way, I could rotate it 180 degrees, or I could go back here and I can use the other end of the normal. I can rotate it again about the normal. Okay, so that's tangency using normals. That's this section. And then finally, there's a kind of a generic way of doing that, which is just building the next cone using the normals, or the next cylinder using the normals. So if I have a cylinder, I'm going to do a cylinder instead. If I have a cylinder, any developable surface, it could also be like a weird surface, cylindrical surface, any surface that is inherently flat. So line, normal, and then I can connect these for an axis and revolve this surface around it. And if those lines are, if they are the same length, if I revolve this last edge about the axis, it'll be a cylinder. And if they are different lengths, revolve, it'll be a cone. And why does this work? Well, it works because essentially that is the structure of two cones or two cylinders that are tangent, originally aligned with their normals. If I were to draw the axis of this cone and extend these normals, they would meet that axis. So what you end up with is the same structure repeated over and over and over again, which is that you can make tangents this way by connecting things in that manner. Okay, so that's how that works. All right, so I would like to go to one more thing here, which is show you making a torus tangent to a surface of revolution, any surface of revolution. So I'll use a different one. Just change this up. Let's revolve this. Okay, and then let's extract an isocurve. And let's go make this transparent so we can see what we're doing. Let's go line normal from this point. And that line will go inside and hit the axis like that, always. So what I can do is I can make a circle 2 point. I can rotate this 90 degrees. And then I can revolve this circle about the same axis. And then I could split the surface of revolution on that circle, and I could split the torus on that circle. They would be smoothly connected to each other. And then if I wanted to go to a flat horizontal line here, if I do this, if I extract an isocurve and I extend a tangent, so curve, extend curve by line, and I go surface sweep one rail, or I just revolve that around the But if I wanted that to go horizontal, what I would need to do is I would need to draw a vertical line here. Go line vertical. And I could go line tangent. And then I could snap here using my perpendicular snap. It's perpendicular to vertical, so it's horizontal. Then I could split that there. I could extract an isocurve like that. Delete this, extend this, revolve about the axis. That is a flat plane. That's like some sort of a strange pit. Okay. So that's that. And then I wanted to show you also there's a this idea of cones that flip. Remember we had looked at this vertical cone. So if I mirror that and extend it and extend it, it's not going to split. Remember, this is this thing again. If I intersect it, I only get the partial intersection. So I have to sort of complete the rest of that intersection on my own. If I put these next to each other, I get this flip-flopping condition. Okay. So that's that. Great. I am going to switch to intersection for a little bit. And then maybe if there's time, I'll come back and look at some of these. So I wanted to show you the torus-torus intersection we were looking at before. So in the penalization exercise, so here's a torus. Torus is made from an axis. So here's the vertical axis. And if I revolve another circle around the vertical axis, I get the torus. So if I put another circle through the center of that circle, and then I make another torus, another circle, like that, and I draw this time an axis this way, revolve this circle about that circle and that circle about that circle And if I intersect these, I get that condition. Of course, I didn't make enough of a hole, so let's do a better job. Revolve, revolve. Getting bigger. So this doesn't have to be constrained in this way. So I'm gonna make this bigger. They don't have to necessarily pass through the centers. That works, or you can rotate this one. Okay, so these are toruses have interesting topology, so they make intersections, and they even make intersections with other shapes that are quite strange. And you can sometimes get interesting things if you force them to align on a point. So if I were to start these two forces the same, so that's like two the same things rotated. But then I just, scale one up a little bit or scale one down a little bit, so that they're going to intersect rather than just pass each other. So if I go here, I go view, set C plane to object, I can draw the axis to this. I could revolve this one around that one, revolve the other one. So you're gonna should have been view, set C plane, world top, revolve this horizontal one. That way, oh, I use the same exact axis. I need to use a different axis or they'll be the same. So let me, I didn't draw the axis in advance, so that's why I use this bigger axis. Now they touch only for a little while, and they come to a perfect meeting point. Get a condition like that. So lots of different weird things depending on how they meet. Okay. So then if I want to look at conic intersections, if I just take a cone and I put it inside another cone like that, I can do a Boolean difference. And there'll be like this just negative cut, or I can do a Boolean difference and get a hole. But if these cones touch perfectly at a spot, you get this weird sort of lariat shape intersection. And I can do that again using the line normal local coordinate system of the surface. So I can go line normal, curve, curve from object, duplicate edge, line normal, and I can align them. They're pointing into each other. But if I rotate it so that they don't, I rotate it so that they are rotated about its normal so that they're intersecting some other way. Then I intersect these, get this crossing lariat, which is pretty unusual. So if I split this, and I split this, it's so precise that it doesn't want to display it. So let's try to make it display it by making the surface into two halves. There we go. Interesting thing, because the opposite surface merges out of the intersection like that. Okay. So then I could also take this intersection and sort of do something with it if I wanted. I could make that, I could make that the start of another tangent thing. So I'd go line tangent from this point, and then I could make a plane goes in there. I could cut that cone. There, and then I get another perfect moment of tangency as this curve turns into that curve. So then maybe I actually lose that moment of the surface. And I instead need to get the isocurve at that spot. So I'm going to untrim this briefly, extract the isocurve, cut it and undo, paste it. And then I can trim this surface layer. I can extend a tangency there. And I can extrude that along the edge. So I know that that's still coming out of that moment of intersection. Okay. So obviously this isn't completely resolved, but you get the idea. All right, so that's that type of condition. And these over here are other sort of paradigms of conic intersections. So, if I have two cones like this, I can extrude this one. If I have a cone at another cone's apex, I can extrude it to a point along its edge. They will intersect in that type of shape. Okay, different paradigms of conic intersection. Okay, so with cylinders, if I have a extruded cylinder and I create a plane that crosses it, and then I mirror it about that plane, I can trim them like that, and they'll intersect, and they'll be the same width. It's like reflecting the cylinder about a plane. So I could do that with a plane at a funny angle. And then go mirror 3-point. I can get something like that. And then what I could do, if I wanted to, let me do a better angle. Let's rotate it the other way. Mirror 3-point. There we go. If I wanted to, I could take these points and also make that extrude this curve to a cone like that as well. If so, once I have this intersection, I can do other things with it. For example, I could align a cone with it. Here's a cone, a little cone. So if I go line, normal, and then I go line, tangent, and somewhere here from first point, line, normal, could put this cone, align its little local coordinate system. Let me get the rest of it. Duplicate edge, arrow, arrow. Here's that, that's the, and then I could rotate this about the normal. To get this little thing to go, put this here, orient 3-point, 1, 2, 3, 1, 2, 3, and then that cone is meeting that like so. So many ways to kind of put things together. Okay, and that's what this stuff is about. Now, okay, so this last thing that I want to go over, this one, and these here, these are based on the Antoine Pevner and Naum Gabo constructions I showed you in class. from the first day and the second day. So those are in the PowerPoints that are uploaded. So these are based on the tangent developables. There are some other tangent developable constructions in the quad panelization file. So this is based on a developable helix. This is based on a developable helicoid. Sorry, this is based on a developable skewed parabola. So what are those? Well, in this construction, there's a helix. It's basically horizontal, and that helix around a curve has a turn of 1 and a radius like the turn of just 1. Radius, I don't know, something like that. Near this so that it remains let me try to do this again. Okay, so set C-plane to perpendicular to curve. Perpendicular to curve. I'm going to make a circle here. And I'll make another circle over here. And let's do a helix around curve. And we should be able to make a helix like that. Okay. This is basically a 1-turn helix that I have here. I don't know why I have it at that funny angle. This is also a 1-turn helix. I see. Mine you see is lying horizontally. This one looks like I rotated it 90 degrees like that. So it's crossing over itself, which obviously it is anyway in some angle, okay? But there we have it, a helix crossing over itself. So let's extend this edge to get the tangent, and then let's sweep one rail. And then let's extend it the other way, split it, surface sweep run rail. Like that. Okay, and then in the this construction, this is mirrored twice, so it's mirrored once about the horizontal plane, and again mirrored about a plane that is perpendicular to its axis. So about that plane in there. So it's also going to be mirrored about that plane. So let's make those planes. Let's extend this. Let's actually just put it on a layer. Now let's extend it a little bit. Sometimes they display better. There we go. Okay. So let's mirror it about this plane. Three point 1, 2, 3. Then let's mirror it the same surface. There you see we have two upside down ones. Let's mirror the same surface again about that sort of halfway plane. Turn off my center snap. Do it right. Mirror 3 point. It looks like I don't have this totally perfectly aligned. So I think my guess is that I probably wanted it to be aligned along this line. So I'm just going to do that manually, orient 2 points. I think that's because I don't have the original helix perfectly horizontal. There we go. So let's take that last thing, And then let's delete this one. Delete the first mirror, paste it. Okay. There we go. Two of them overlapping. And then I can just extend these out, draw like a trimming shape, which I think is going to be yeah, just orthogonal to this internal coordinate system. So let's just draw a rectangle. So let's make this horizontal. So I can do that by transform orient 3-point. And then just hold shift, actually turn on project. So it's like the same, but horizontal. Make a box sort of in there. And extrude this box both sides. Looks a little big to me. I'm going to scale 2D. Let's just extend these surfaces until they go through the box. Right, let's split this. Delete the leftover. Okay, well, I don't have it aligned exactly right. But he's obviously pulled it in so that this intersection here, I think, is sort of controlling it. His is trimmed a little smaller, but actually, I think this is potentially more interesting. Look at it for a second. If I were to bring this trimming in to layer, it won't trim because it's right on the edge. So let's just make it slightly bigger. Okay. So what I think is, so it took me a while to figure this out. I've been looking at this shape for many years. But what I think is interesting is that it's just two shapes mirrored and trimmed. And that is the idea, that if you mirror two shapes, you put them next to each other in a way where they're aligned along some line, and then you trim them, you can get something pretty remarkable pretty quickly. The other thing about these surfaces is these tangent developables is they have this trouble displaying. So if you want to build them, you really do need to divide them by their isocurves down, and then split them and then unroll them. So if you split it into multiple surfaces, um, you know, based on a small increment, like this. And then you select all of these. And you rebuild those by something that isn't like a degree 1 surface. I have to shrink them first. Then I can join those, and then I can unroll them. Like that. And they won't unroll perfectly, but I can get a surface like that. So that's the first one. Then the second one is based on the skew parabola, which is very interesting thing, which is that a hypar a parabola extruded. I just used the parabola command. I'm going to scale this so it aligns with the hypar I'm using. And also a cone. So that would be a right cone. I just take a I just take normal to this little axis here, and I rotate this 45 degrees. And I go view, set the C-plane perpendicular to curve, and make a plane here. I find the points where that plane intersects that axis. Do a circle 2 point. That circle will be centered around this plane and be evenly equaling those. I can put that cone there. I can rotate it around. This particular cone, that hypar and that parabola all intersect along a line that they share. That line is called the skew parabola. And that line, if I get it by intersecting the hypar of the cone, you notice they won't perfectly intersect because they're diminishing to 0. So in order to get the intersection, I can rebuild the hypar and rebuild the cone as like surfaces with more points. Let's do that again. Intersect them, and then I'll get closer. And then I can cell last, delete these and undo them, and paste. And I can extend them. To try to extend them until they meet. I can also, in this case, I happen to know that I can just get it that way too, but I'm going to try to do it the hard way for you guys. There they are. I'm going to just sort of like vaguely bring them together. And I would be able to split these surfaces with that curve. Okay, so there's that curve. By the way, this curve, extend curve by line, could also be uses to create a tangent developable. So I don't know what to say about this. This is just like too many surfaces in one moment interacting with each other. But I feel like there's some potential there for something amazing. Um, this um, sort of oddly not working super well. So let's use the other one there. And let's extend the tangent. The sweep run rail. There we go. Okay. And let's get the opposite one. That's just a lot of surfaces all sharing an intersection. An unbelievable amount of surfaces sharing an intersection. Okay, but it turns out that Antoine Pevsner, who's sort of the master of tangent developables, does in fact use this for another one of his sculptures. He takes it over here. This is the same curve, and again, uh, what it's sort of reoriented in space, not vertical like this, but in fact up and down like that. So in order to do that, all of this stuff is just about me trying to do that. So I think what I did is I made a coordinate system here. Um, I think I rotated this 90 degrees vertically. Let's see if that is in fact what I did. Um, and then I think I also let's see which one I actually used. Yeah, that's all I did. Okay, so then I took this and extended a tangent. And we can go surface, sweep, run rail, and we can extend the other tangent. Surface, sweep, run rail. Get that crazy looking thing. And then I yeah. Okay. Then it's just trimmed. Okay. So this is this crazy thing. And then we can make a box in here. And we can rotate that box just like we did last time to align. Let's look at it from the top view. there's this sort of intrinsic axis in here. So we can rotate this box to align with that. It won't do it because I have apparent intersections turned off. So let's just draw it this way. Project on. Okay, so I have this box, and I'm going to also make a horizontal plane. And let's try splitting this. Okay. And then I don't know that I don't think I did it in the right spot. I think it needs to be, first of all, longer so that this meets the ground. Meets the ground. Second of all, it needs to be deeper in this direction. And in that direction. Let's try that. Better. All right, let's hide everything else here. Okay, so then there's that. So the next thing that's happened here is sort of amazing, which is that there's a tangent extended here. And there's also a, I think a tangent extended here. Okay. And then there's a surface that's twisted, actually, put in, like two twisted surfaces. Why am I showing you this? Well, it's interesting because it would have been the obvious thing to do to just try to make a plane here, because that is, what would have been tangent. But it doesn't really get us anywhere. So, or you could have tried to make a twisted surface here, which I think was his first thought. But it naturally sort of reverts to this plane. So in order to get it to be something that sort of self-intersects, he kind of made a twisted surface like that and then reconnected it with another twisted surface, which I think is interesting because it shows you that, maybe you don't have to always make everything tangent. If you're searching for something, you can potentially um, discover something in a different way. So the other reason I'm showing it to you is because these hypars, they look very different depending on whether if you have the points in the same corners, but you move them around. So that hypar is very different um, than this hypar, obviously. And so often I make the wrong one, and then I need to move the points uh, to the other side. Okay. And then this surface, I think, is I lost my box, so I'm gonna copy this and go back. The surface, I think, is just like extended. Actually, I think it's something like that, and then it's also split with the same box, and then you can mirror it. Leave the box. And then this whole thing is oh, actually, I did something wrong. I'm sorry. This, before it's split, okay, this is really interesting. This point, I think, if I continue, if I take this point, I just keep moving it out. It changes the way the hypar trims. So if I split this now, it'll almost be tangent. And then I can take this and mirror it. Mirror it again. And then this whole thing is scale 1 bead. Like so.